Okay, I'm gonna go over quiz 3 practice 2. So this is in prep for quiz 3, practice quiz 2, and I will solve it here to show you what the reasoning for this one looks like. Okay, so we're told we have one vector that's pointing north that has a magnitude of 4 newtons, one vector that has a magnitude of 10 newtons and is pointing 30 degrees north of west, as shown in the diagram. And then we know that there is a third force with a magnitude of 15 newtons, but we don't know which direction it is pointing. The last thing we are told is that the net force points south. So I can draw that in here. F net points south, but we don't know its magnitude. So this isn't to scale. This F net could be way down here, or it could be very short, but we know it only has a y component, and that y component is negative. So we can do that for all of them. We can write here F net, which is F net x, F net y. So just breaking it down into these x and y components, then F net x is 0, because it's only up and down, and F net y is negative, but we don't know what that value is. For this one, which we'll call F1, its components are, well, it also has no x component since it's only north, only up. So I'm just going to write this up here. Its x is 0 and its y is positive 4 newtons. We'll put a little plus there because it's going up. And then for this other force here, we'll call this F2. It also has some F2x and F2y. And we know its magnitude and direction, so we can find these two things, but we'll need to do a little trig for that. But for now, let's just notice the sign of each of those things. F2x, the horizontal component of this one, which would look like that, is negative. It's pointing in the negative x direction, so that is negative. And F2y, which is the vertical component of this, is pointing up. So that's a positive number. Right, so you can see here, each vector breaks down into a x and a y component. They can be drawn like this as a right triangle, and we can find what those components are based on the magnitude and direction, as well as the other way around. Find the magnitude and direction from the components. Okay, so what we want to find is what direction F3 points in, given its magnitude. So as always with these problems, let's break it down into an x and into a y, and then we'll put them all back together at the end. So first, just our x components. We know that F net x, the most general we can write this is just F net x equals F1x plus F2x plus F3x. I haven't really used any information here. I just said that the sum of all the x components is the sum of all the x components. And then I know some of these. I know that F net x is 0 because it only points south, so it only has a y component, so 0 equals F1x is also 0, as we found, since it also only has a y component, so that goes away. F2x is this thing that we're going to have to find, but we can, but that's non-zero, and it's going to be a negative number, we know that, and then plus F3x, which is something that we need. So this allows us to find that F2x equals negative F3x. So the x components of vectors F2 and F3 are equal and opposite. We know that has to be true, because if our net has no x component, and F2 has this negative x component here, whatever F3 does, it must have a positive x component that cancels it out, so that the total can be in the y direction only. So we don't know whether it's going to be pointing north or south yet, but F3 is going to be pointing in general to the east or to the right in the positive x direction. Let's find out exactly what that value is here. Like I said, F2x we can find based on the trig. So we know the magnitude is 10 and it's 30 degrees above the west, like it's 30 degrees north of west. So here we are going to use cosine. So this leg here is the x component, this is F2x, and it is adjacent to the angle we were given. It doesn't have to be cosine just because it's x. If we were given this angle here between f2 and the y-axis, we would instead use sine for the x, but we're not. We're given this 30-degree angle, so we'll use cosine. So f2x is equal to 10 newtons times cosine of 30 degrees. And finally, we need the sine for that, right? We know it is pointing to the west, or the negative x-axis. So f2x is negative 10 newtons times cos 30. So always be careful with your signs, and whatever answer you get, check to make sure it agrees with your diagram or your qualitative understanding. And now we know f3x is just negative f2x. So if f2 is negative, f3 is positive, like we just said. So f3x is just going to be positive 10 newtons times cos 30 degrees. And that works out to be equal to, what is it? I don't actually have it right here, but I think cosine of 30 degrees is something like 0.86, perhaps. We'll solve that after, but this is good for now. Here's our x component of f3. So now let's go for our y component. So same type of equation up here, f net y equals f1y plus f2y plus f3y. Just saying that all the individual y components add up to the net. F net y is negative. We know that. We don't know its magnitude, but we know that's negative. So we'll just leave it as f net y. F1y, we know that is positive 4 newtons. F2y, we'll have to get using trig, the same, very similar to how we did for the x component, except now we will use sine for the y component, and that is positive because it's pointing upward in the y direction, north. So that's going to be plus 10 newtons times sine of 30. So that gives us this component here. And then finally plus our f3y, which of course we do not know yet, but that is what we want to find in this problem. So we're left with a little bit of an issue here, which is that we have two unknowns in this. We have f net y and f3y, neither of which we know. We know f net y is negative, and we know that these two things are positive, this 4 newtons and 10 sine 30. So that does tell us one thing, that f3y is also going to be negative, right? Because if we want this plus this plus this to be a negative number, then positive, positive, this has to be negative. So now qualitatively, we know we said f3 points in the positive x direction, and now we just figured out it points in the negative y direction. So it's going to be pointing somewhere in this southeast quadrant here. Positive x, negative y. So I'll just move this for now here, just so we can draw a vector. Again, this is not to scale yet, but we know that is our f3. And we also know its magnitude. We started off with that. We know that its magnitude is 15 newtons. So that gives us the key information we were missing to find what f3y is, or we can just actually don't really need f3y, we can just go straight for the direction. What I mean by that is, well, we know its x component, right? We know that exactly. So this x component here, just however far f3 goes in the x direction, is 10 newtons times cos 30. And we know its magnitude, so I'm just going to move the f net over here. This vector here is f net. But we also know its magnitude of f3. This is 15 newtons. So now I have what I need to find what this angle, I'll call it theta, is there, which is what the question wants. It wants the direction of f3, right? So here I have my hypotenuse, and my adjacent side. So that means we're going to use cosine. And in this case, we're going to have to use inverse eventually, but we're left with cosine of theta. So the cosine of this angle here is equal to the adjacent, 10 newtons cos 30, over the hypotenuse, which is 15 newtons. So then theta, taking inverse cosine of both sides, is just inverse cos of 10 newtons cos 30 over 15 newtons. I prefer to solve problems this way, where I write everything out before I plug it into my calculator, so I'm not carrying around all these weird decimals and stuff, but that's completely up to you. And when you plug all this in, inverse cosine of 10 newtons times cos 30 over 15 newtons, you should get that theta equals 54.7 degrees. So now we're almost done, but this isn't quite enough. If we're just going to circle this, it's not quite enough because it could be 57.4 degrees from anywhere. Specifically, we said this is our theta, so I could say this is 54.7 degrees. I could say south of east, right? That's one way to put it. Here's east, and I go south of it. I could say below the positive x-axis. That's another way to say it. Here's my x-axis, I'm below it. I could say clockwise, past the x-axis, however you want to say it. But you need, if you're going to just give an angle, you need to say what that angle is in relation to. So final answer will say 54.7 degrees south of east is this F3. And clearly this isn't to scale, but it does generally point in this quadrant. Okay, so now it asks to find the magnitude of the net force. So I'm going to get rid of the work I did for the x component up here. Now we want to find our net force. Why did I get rid of the x component work? Well, because the net force we already know only points in the y direction, right? Its x component is 0. So we're already all set with that. The magnitude then, our F net magnitude, which is equal to the square root of F net x squared plus F net y squared. Since F net x is 0, this is just equal to F net y, right? If a vector is entirely in the y direction or entirely in the x direction, its magnitude will just be the length of that one component that it has, right? So we need the magnitude or just F net y. And we've already written out our equation down here for what F net y is. It's the sum of the F1 x component plus the F2 x component. Now we just need to pop in our F3, sorry, I meant to say y that whole time. This F net y is the F1y plus F2y. We just need to plug in our F3y, which we can find now because we know the magnitude and the direction. So my y component of F3 is pointing down, right? F3 points south, well, southeast. So this needs to be a negative 15 newtons. And then since we want the y component here, it's going to be sine, because that is opposite of the angle we're given. Again, in this problem it works out, but sine is not always for the y component. It depends what angle you're given. Here it is. So 15 newtons times sine, and now we know that angle is 54.7 degrees. So now our F net y is just the sum of these three things, for like positive plus positive, and then some negative, and those things work out to be F net y equals negative 3.24 newtons. That's just plugging in these things into a calculator, and we get F net y is negative 3.24 newtons, which, as we found above, means that the magnitude of F net is 3.4 newtons. Being very careful that when we list a magnitude, it is positive. So I guess this is a little misleading here, just saying that the magnitude of F net is equal to F net y. When I square something and take the square root, my answer is always going to be positive. So even though we know that the y component of f net, sorry, this is f net here, we know that the y component is negative, its magnitude is just a length, right? So I would say this magnitude, and then if I wanted to tack on the direction, I would say this south. But it's incorrect to write a magnitude is negative. So there's our magnitude for the net force. And then finally, question 3. After the net force acts on the object is moving north. Did this force result in an increase, decrease, or no change in the speed of the object? Okay, so the net force acts on it south, right? We know the net force is pointing south, and we want to know how this affects the object so afterward it's moving north. Let's use a momentum chart. I'm already getting tripped up on my words here, which is a great time to use a tool like a momentum chart that helps us organize these things. So it's a simple one. We just have one object. So we have P initial, delta P, P final, and we just have our single object. I'll call it O1. And in this case, we have an open system because there is an F net. We know the F net is this 3.24 newtons south. And so if we do have an F net, our delta P is not going to be 0. In fact, we know exactly our delta P is equal to F net delta T. So times whatever time, how long the force was applied. We don't know exactly what this delta T is, but it is just some number, some amount of seconds that's positive. And so whatever direction our F net is the same direction as our delta P. If our F net is south, our delta P is south. And I think that makes sense intuitively. All we're saying is that if we push an object down, the change in momentum will be down. So our delta P here is down, just like our F net. We're also told that after this happens, so P final, the object is moving to the north. So our P final is up. And we want to know, well, let's finish this momentum chart first. If we know our delta P and our P final, we can get our P initial, right? So I'm going to erase this work here. We don't need our numbers anymore. But we know P initial plus delta P equals P final. In this case, we want P initial, so I'll move delta P over to the other side. P initial is just P final minus delta P. And I wrote this out algebraically, but we can just do this using our vector addition, right? So for that, instead of using subtraction, it's easier to write this as PF plus negative delta P. And now we just put in PF, which is a vector pointing up, plus negative delta P. Since delta P is pointing down, then negative delta P is just that same vector, but flipped around, pointing up. And then we're left with an up arrow, plus an up arrow is, of course, just a longer up arrow. That's these two plus each other. So my initial is a longer up arrow. So the answer would be that, this still isn't our answer. So we know that here's my initial momentum, and here's our final. The question asks specifically, did this force result in an increase, decrease, or no change in the speed? So last thing we have to do here is figure out where speed fits in here. I have momentum. What about speed? We know momentum is equal to, so I'm going to erase this now because we've made use of this equation. We know momentum, not delta P here, but just P, is equal to mv, mass times velocity. And in this case, we can just use, so I did something very important here. I could write these as, if I want to really show that they're magnitudes. But in this case, we're only dealing with one dimension. We're just dealing with up and down. This is an object moving up, a force acting down. And so I'm going to use magnitudes here. Right, we can just use plus and minus instead of x and y directions. Anyway, whatever direction my momentum changes, or whatever direction my momentum is, my velocity is the same, right? So an object moving to the east has a velocity pointing to the east and a momentum pointing to the east, because we're just taking that velocity arrow and multiplying it by some mass m, which just stretches the arrow. It doesn't change its direction. An object is moving down, its momentum is pointing down, its velocity is pointing down, and if it's whatever its velocity is, speed is the magnitude of that. So if we want to know what happened to its speed, what we're really asking is what happened to the magnitude of its velocity. And so we know that momentum tells us about velocity, right? Velocity points in the same direction, just rescales these arrows. So if my initial momentum was pointing up with a big arrow, and my final momentum was pointing up with a smaller arrow, the same must be true with my v initial and my v final, right? If I just multiplied these by m, then I'd get my momentum arrows. But we're concerned with velocity. And then finally, we want to know what happened to the magnitude. Well, it shrank, right? We see that our final velocity is shorter than our initial velocity. So the speed decreased, which would be the answer to that part. That was a lot of talking in words, when it might be easier just to see this intuitively as well. What we're saying is that an object was moving up, and then we applied a force to it, down, but it wasn't enough to change its direction, it just slowed it down. So an object is moving up, we apply a force on it that slows it down, and then after the force is applied, the object is still moving up, but a bit slower. So the speed did decrease. So there's a couple things in there. I think the most important is to realize that F-net changes our momentum. It doesn't mean that our momentum is in the direction of F-net. It means our change in momentum is in the direction of F-net. So it's very important that F-net delta t equals delta p. This delta is super important, because like we saw here, F-net is down. F-net points down, but our p is up, both initial and final. Our delta p is the thing that's pointing down. So anyway, F-net causes a change in momentum, and that change in momentum occurs in the same direction as our change in velocity. So in this case, the force just slowed the object down. So hopefully, yeah, this wouldn't take as long if we were just solving it without finding every little nook and cranny of this problem, but I wanted to give you a very detailed solution.